Hi everybody, welcome to the last section in Calculus 2. Yes, that's correct. This is the last section in Calculus 2. Even though we don't have much calculus here, this is just a review in pre-calculus. So conic section. What we have is a double cone. So the cone, this is just the surface of the cone. We're not talking about the interior of the cone. So there's no interior. So I have the cone. And then we will have a plane intersecting that. So, and in this case, the conics that we study do not contain the vertex of the double cone. So when we have a plane intersect a double cone, we will have the intersection in this shape. And those shapes, we have circle, ellipse, but both of them can consider to be just ellipse, parabola, and a hyperbola. Right. So that's one way to define the conic section. A more mathematically definition of conic section, we define that based on this definition here. So a parabola is the collection of all the points in the plane that are equidistant from a fixed point f to the point to the line D, from fixed point F as down from the line D. So pretty much what we have is the fixed point here, F, and that is called the focus. So we have a fixed point and a line that is also fixed. So those two things are given, and this is called the directrix D. And the definition of an ellipse is the set of all the points that are equidistant to the focus and to the directrix. So if we have the distance from this point to the directrix, this distance will be the same as the distance from that point to the focus. We might have another point here. Let's say if we have this point, then this point, the distance to the focus and the distance to the directrix, these two distances are the same. And then we might have a distance from this point to the focus and to the directrix, they are the same. And then it's a bunch of all of the points that satisfy this condition belongs to a parabola. So we have a parabola. And finally, mathematically, when we talk about the equation of a parabola, will be in this form. So, and the nice thing about this is we do not have, we only study the case where the simple case where we have the vertex at the origin. Yeah. So see the vertex, all of the vertex at the origin. So that's the simple case. And the focus and the directrix will be given, but the equation will be in that form. So what we have here is, if we have the y square then we will have the parabola that open left or right. Whether left or right will be determined by this negative side or positive side. So y square, this is going to be horizontal. So horizontal. If we lead in with y square, if we lead with x square, it will be up or down. Depends on if there's a minus or not. And this will be vertical. Right. So start with y square, open left or right. Start up with x square, open up or down, like y equal x square up, y equal negative x square down. And then in the formula we have 4px or 4by. If we have y square, we end up with x. If we have x square, we end up with y, and then 4p. P is the distance from the focus to the directrix, and P is the distance from the vertex to the directrix, or from the vertex to the focus. So P is here, distance from the vertex to the directrix, and the distance from the vertex to the focus. And we also have at the point where it go through, where it go parallel to the directrix and go to the focus, we have this is the length of the lattice rectum equal to 4p. So first of all, this to write somewhere. So P from the vertex to directrix. We're talking about absolute values, just to be clear. Or from vertex to focus. And the length of the lattice rectum that go to the focus parallel to the directrix is going to be 4p. Where do I put this? Let's see. So that, length of lattice rectum will be this is 4 absolute values of p. So it will be this much. Right. So y square or x square. If we have y square, then we end up with x. If we have x square, we end up with y, and then 4p, and then positive or negative. Positive is open up or to the right. Negative is open down or to the left. Right. So let's look at first example. Find the focus and the directrix of the parabola y square equal to negative 8x. Now this is y square. Let's just do reasoning here. If it is y square, this of course is horizontal. Horizontal parabola, the negative, meaning that it open to the left. And in general, we can say what we have is y square equal to ax negative ax compared to the form y square equal to negative 4px. Matching this from here, we can say that p is equal to, negative 8 equal to negative 4p, so p is equal to 2. So the distance from the vertex to the focus and the vertex to the directrix is 2. Right. So all of this, the vertex of the parabola is going to be at here, 0, 0. Now it open to the left. So it will be like this. So the vertex will be right at the focus, right at the origin, sorry. Now this open to the left, meaning that the focus is on the left. It go around the focus. The graph always go around the focus, away from the directrix. So the distance is 2, so we go 2 units to the left, because that's what it said, and that is the focus. 2 units to the left from that point, which means x equal to -2 and y equal to 0. That's the vertex. The directrix is the line that on the opposite direction from the focus, and we also go 2 to the left for the focus and 2 to the right for the directrix. And since this is horizontal, the directrix is going to be the vertical line at 2. So this is 2, the directrix. This equation go to 2, so we have x equal to 2. Right. And then we just graph. To graph the parabola, all we do is just go around the focus through the vertex, away from the directrix. But the way we graph it, actually, it will help if we use the length of the lattice rectum. So if this is 2, we know it's going to be like this. But the distance where we go through the focus is going to be 4 times p. So if p is equal to 2, so the length of the lattice rectum uh, 4 times absolute p, which is 8. 4 times 2 is 8. So we go through the focus. It is 8 in total, meaning that we go 4 up and 4 down. That is the length of the lattice rectum. And then the parabola, we go to those 3 points. Right, so it's just a sketch of the parabola. Right, so that's what we have. Right, so it's always helpful if we just put everything here on the graph. So again, vertex in the middle, focus on one side, directrix on the other side. The graph will go around the vertex, around the focus, away from the directrix. So that's what we have. Right. Next, find the equation of parabola with the vertex at 0, 0. So we still have the vertex here. Open down and passes through the point 2 and -3. So first of all, we do not have anything. We just have a point. It goes through 2 and -3. That's all we are given. Actually, we are also given this is open down. So it's open down, meaning it's going to be x squared, because that's vertical and down. So if it's vertical, we will have x squared leading, and it open down, it's going to be -4 py. So we start with x squared because it is a vertical, and this negative, it's open down, and x squared, so it's vertical. If we have y squared, it's going to be horizontal. Right. And then we just need to determine p. Good thing that we have 2 and negative 3 here. So I will substitute 2 and negative 3. Into the equation. So x is negative 3. Sorry, x is 2. Y is negative 3. So x is 2, y is negative 3. And we do that. Put in the equation, we will have 4 equal to 12p. So p is equal to 1/3. So the equation is x squared equal to negative 4 py, and we just need to substitute the 1/3 here. So x squared is 4 times 1/3 y, or we write x squared equal to negative 4 over 3. Negative 4 over 3 y. Right. So if we want to draw, we just have a point here. Because it's a symmetry, it will have another point here. Sorry. Negative 2 and 3. It opened down, so with symmetry, it's got the line symmetry will go to the vertex, and the focus will be 1/3 away from it. So the focus will be very close here, and the directrix will be 1/3 up, and it will go to the point 2 and negative 3. So the parabola will be like that. Yeah. So p is 1/3, so it'll go 1/3 down from the vertex. We have the focus, and 1/3 up. We have the directrix. So that is the parabola. Right. And we have to tell about the application of the parabola. I mean, on all of this conic section, each of them have some certain application, but none of them have more application than the parabola. So there's the properties of the parabola like this. If we have a parabolic surface, so this is the parabolic surface. It says that if the line parallel to a particle, I mean, parabola have property that's make useful. So, a particle approaching a parabola of any line parallel to the axis of the parabola. So we have the axis of the parabola, the axis that go through the vertex and the directrix, vertex and focus. So you have this line that go through the vertex and the focus. So we have a focus here, and the vertex here, the line that go through the vertex and focus. Now, any line that is parallel to this, if it's parallel to that axis, when it hit the surface, it will bounce to the focus. Doesn't matter how it goes. If it parallel to the axis, it will go through the focus, and at the same time, if it go through the focus, when it hit the surface, it will bounce parallel to it. So there are two ways to do this. If we put the light source here and the parabolic lens, we allow the line to be parallel to it. So if we have the parabolic lens and we put the light source here, all the line will be parallel to it. And the parallel line that will travel further distance than the line that is not. So one way to do that. Another way to do that is to build a center line. We have the receiver right from the focus, and any ray that is parallel to the axis, when it hit the parabolic surface, it will go to the focus. So the focus here will receive on the line that parallel, on the signal that parallel, that hit the surface of the parabolic surface. So from the focus, strike the surface, and then parallel on the parallel lines, strike the surface and go to the focus. Where they will put the light source here to emit the light out, or where they will put a receiver there to receive the parallel source. An application to this is if we have the parabolic surface here and we put a fire, something that can catch fire, and you put this under the sunlight. The sunlight consists of parallel ray, and the line will those parallel line will hit the surface and go through focus into that point. And because the sunlight also have heat in it, so it will focus on the light and all the heat at that point, and essentially it can catch fire at the focus. Right, so just want to talk about that in the application of parabola. Right, next we go to another one, ellipse. Right, ellipse. Definition. Ellipse is the collection of all the points in the plane where the sum of the distance to two fixed points. So this time we have two fixed points. Each of them is a focus. So together, the plural is foci. So we have two foci. And then an ellipse is the collection of all the points where the sum of the distances from the point to the foci, the sum of that will be the same. So you're going to add this one and this one. It is the same as where we start from here. That distance plus this distance. The total distance here and here will be the same. Doesn't matter where we have the point. It could be here. The total distance will be constant. That is an ellipse. The set of all the points where the sum of distances to the foci are constant. Right. And an application of an ellipse is that it's not as much as an application compared to the parabola, but if we have the elliptical surface, when we put a light source here from one focus, when it strikes the surface, it will bounce to the other surface. It bounces to the other focus. So we'll go from one focus, strike the surface, and go to the other focus. So think about this. If we have an ellipse, actually have a ruler that can draw the ellipse. So let's say we have an ellipse like this and two foci. Think about this. Let's say if we build a pool table with two holes at the foci. So if we have the ball here, how do we hit the ball to this hole? Right. The way we do this is we always aim from the hole, strike the surface. It will go to the other hole. That is the properties. From one focus, strike the surface, will go to the other focus. That is the properties of an ellipse. But the definition is the total distance is going to be equal to a constant. The total distance are constant, not each one of them, to the total. Right. Having said that, when we draw an ellipse, if we have a string, then we can do that. So the way we do that, we have two fixed points for two foci, and then we have a string. The string is longer than twice the distance here, and then you put the string. As long as we keep the tension on the string, we trace around, and we should be able to draw an ellipse. But having said that, is not the way we draw an ellipse. The characteristic of an ellipse is that I can work just either one of this. We might have horizontal or vertical. It doesn't matter. But one of what we study here is the center at 0, 0. So we have center at 0, 0. We might have vertical or horizontal, doesn't matter. But if we have horizontal, two foci will be left and right of it, and the distance is c away from it. So we have two foci. So we define c from the center to a focus. And then from the center to a vertex, we call that distance A. And we will have the relation. In an ellipse, A is going to be the biggest distance from the center to the ellipse. A is the biggest distance. So we could write like this, or we can write A square equal B square plus C square. So A is the distance from the center to the vertex, and C is the distance from the center to the focus. And what is B? Well, remember, A is the biggest distance from the center to an ellipse, and that is the focus. And B is the smallest distance from the center to the ellipse. So this is the shortest distance from the center to the ellipse. C, shortest distance from center to the ellipse. And when we put them together, we have the equation x squared over a squared plus y squared over b squared, or this. It doesn't matter where we have a and b, but knowing that whatever below the a, whatever below x, is going to be horizontal. Whatever below the y is going to be vertical, and then we're going to graph. It will be easy when we go to an example, but the things that are constant in here that are the same on both of this. A square is the biggest distance from the center to the vertex, which is the biggest distance from the center to the ellipse as well. C is the center to focus, and B is the shortest distance from the center to the ellipse. Right, so A, B, or really doesn't matter. Right, now, like I said, those three things will be the same. That will be the same. The equation may change. Right, so first when we look at this, x squared over 9, y squared over 4, that means on horizontal, because 9 below the x squared, horizontally it will be longer than vertical. So this is going to be the horizontal ellipse. Now if we want to draw it, it's actually easier to draw it. The center will be at 0, 0. And we have x squared over 9. So we take the square root of this. We have 3. And that is the horizontal distance. 3 to the left and 3 to the right. Take the square root of that. And then we take the square root of this. Square root of 4, which is 2. And that is the vertical distance. 2 up, 2 down. So I'm going to draw a box. 3 up, 3 left, 3 right, because from the equation, that's what we have. And 2 up, 2 down. Because we have 4 below the y square. And the ellipse will be inside this box. Right, so that is an ellipse. So it's easy to draw. Square root of x, whatever inside below the x square, take the square root. Whatever below y square, take the square root. And in that case, we have the box, and then we have the ellipse. Now, the distance from the center to the vertex is the longest distance. So from here on out, that is A, the longest distance. And the shortest distance from the center to an ellipse is going to be B. The shortest distance from the center to the ellipse is 2. So that's why in this, the total distance is called the major axis, because that is the biggest distance that can fit inside the ellipse is 6. The biggest line, think about this, we're trying to put a line inside here. The biggest distance we can put here is 6. The major axis twice as that, and the smallest distance, the smallest line that we can hit the surface that go through the center is going to be that. It's called the minor axis. The shortest line that go through the center and touch the ellipse. So if we have any random line like this, that line will be shorter than the major axis and longer than the minor axis. The shortest one is where it go through where it is perpendicular to the major axis. Right, so that is B equal to 2. Now if A is 3, B is 2, Pythagorean relation. So we can solve for that. We can solve for C. So A squared plus equal to B squared plus C squared, because A is the biggest distance. So we have that, A squared by itself. 3 squared equal to 2 squared plus c square. So we can solve for c square, and c is square root of that. So from the center, we will have square root of 5. Away from the center, we have a focus. So square root of 5 is about 2.2. So we have one focus here and one focus there. The focus, the foci, and the vertices must be on the major axis. So all of them are aligned like this. So the center, 2 vertices, 2 foci, and center, all of them on the same line. Right, so we have the equation, and that is the graph. Now we're going to write out everything about this ellipse. First of all, the center at 0, 0. By the way, if we don't have the center at 0, 0, this equation will change to x minus h squared over a squared y minus k squared of b squared equal to 1. So it will, the center will be at h and k. So that's just a translation there. That in Greek calculus. But for now, we studied a simple case where the center at 0, 0. Right, foci, 2 of them. One is square root of 5, negative square root of 5, and 0. So square root of 5 from the center, and then square root of 5 and 0. So square root of 5 left and right, we have the foci. Vertices, from the center, 3 left and 3 right, so negative 3 and 0, and 3 and 0. So let's see, we have vertices, foci, and center, of course, and the length of the major axis. So major axis, the line that go through the center, the longest line that go through the center and touch the ellipse, it's going to be twice. It's going to be 6. And the length of the minor axis is the length of the minor axis is 2b, which is 4. So the shortest line that go through the center and touch the ellipse is going to be 4. The longest line is going to be 6. Right. So that's what we have. So it's easy to graph it based on this fact, right? The major axis, minor axis, we can draw an ellipse. Right. And always draw the box first, and then we can draw an ellipse inside. That will be better. Right. So we have that. Next, find the equation of ellipse, center at the origin. So first of all, center at 0, 0. With the foci on the y-axis. So the foci will be here, and the length of the major axis is 8 and minor axis is 4. By the way, if the foci on the y-axis, meaning that this is going to be the vertical ellipse. So the foci on y-axis mean it will be on the y-axis, so everything will be a vertical ellipse. Then the major axis, length of major axis is 8 and minor axis is 4. So length of major axis is 2a, but it is equal to 8, so a is 4, and the length of minor axis 2b is 4, meaning b is going to be 2. Right, so based on that, on the graph, we know this is going to be vertical, so we're going to be 4 up and 4 down is the major axis is going to be vertical as well. Because this is a vertical ellipse. So, meaning we go 4 up and 4 down. And 2 left and then 2 right. Raw box first. Right, and then the ellipse will be inside this box. Now, so the ellipse like that. Now, the biggest distance from the center to the ellipse is going to be 4. So in that case, we have the vertex here and here. For up, for down, so the corner will be x equal to 0, y equal to 4, and x equal to 0, y equal to negative 4. Negative 4, yes. For up, for down. And this is nothing at all, but we know A and 4, B is 2, we can find C. A is the biggest one by itself. So A, we're going to put 4 square here. B we know is 2 square, and C square we don't know, but we can solve for it. It's going to be 12, and C is square root of 12. Meaning that if we want to find the focus, will be square root of 12 up, plus square root of 12 is about 3 point something, right? 3.45. So here we go square root of 12 up and square root of 12 down. That gives us the focus. This distance is square root of 12. So we can actually write the two foci. One of them is x equal to 0 square root of 12 up, x equal to 0 negative square root of 12 down. So that's all the information about the ellipse. So 2 vertices, 2 foci, and the center, all of them will align on the major axis. The minor axis doesn't consist of anything. Right. So it will be helpful when we draw ellipse, we draw the box like that. Right. Now we go to the third one is the hyperbola. Right. So hyperbola is the collection of all the points in the plane whose the distance of 2 fixed points on foci is constant. So first of all, we have 2 foci. And the definition here is the differences of the distance to the foci to a point is going to be constant. So if we have the point, let's say this point here, the distance from that point to the first focus and to the second focus, if we subtract the two, it's always a constant. So take this one minus that, that's going to be constant. Same thing here. if we have, let's say, this point, take the bigger distance minus the little distance, that will also have a constant as long as the differences are the same. The differences of the distances are constant. Those points belong to the parabola. I'm sorry, hyperbola. That's what we have here. Right. Now, to actually draw this, we will have an axis that go through two foci and two vertices, and this called the transverse axis. Transverse. Yes, that's called the transverse axis. So we have two foci there, and the centers there, and two four vertices also there. But the way we draw this, whether it's vertical or horizontal, kind of difficult to draw this without any guideline, right? So this is what we do. First, we have the center. In both of these cases, our center at the origin at 0, 0. So this is a simple case. The center two vertices always belong to the conics. Vertices belongs to parabola, ellipse, and hyperbola. So always belongs to the conics. So we have two vertices there, V2 and V1. And the distance from the center to the vertex, what do we call that? Distance from the center to the vertex, that is A, right? Center to vertex is A. So we call A center to vertex. And then C, distance from the center to focus. In this case, C is the longest distance. And then we still have B. So what is B? So actually B is going to be the distance that is perpendicular to the transverse axis. So in that case, this is B. Kind of difficult to describe it, but it's just perpendicular to the transverse axis, and we'll go up and down that much unit. So we're going to have the box still the same thing as before. So we have the box. B up and down, A left and right. Now the ellipse will fit inside the box, but the hyperbola we will have two lines here called the asymptotes of the hyperbola. Go through the diagonals of the box. The asymptotes, and so the asymptotes rise over run. So asymptotes in this case is going to be rise over run. So depends what we have here. It could be A over B or B over A. So y equal to rise over run times x. Will be plus or minus. That gives us the asymptotes. Right. Similarly, on here we have from the center to the vertex. So this is going to be A, and C is the distance from the center to the focus. And B is going to be the one perpendicular to it. So, let's see. Right, about here. Then we can draw the box. And then the diagonals. And then the hyperbola will be fit approaching to the parabola, to the asymptotes, sorry. Approaching to the asymptotes and go through the vertices. Right. Now it was to talk about a list and application of hyperbola. So the way we use this is using the GPS system. So think about this. I'm talking about the two-dimensional case, the easier one. Let's say there's a lining at this point. Two people here at F1 and F2. The lining source will be right there. So when we hear the lining, we can measure the distance when we see the lining, and then we measure the distance. When we see it first, we see the lining, and then we listen, we heard the lining, so that we have some certain time here. So there's the distance from where the lining is to that person. And then both of them should see the lining at the same time, because light travel extremely fast compared to sound. But this person's further away from the lightning strike, so he will hear the thunder a little bit later. So we're going to have this distance D1 and this distance D2. Right. So how do we determine the location of the lightning, where the lightning strike? So the way to do this is the total the difference between the two. So we take the difference of the two. We know that the lightning must belong to the hyperbola, because the distance between those two must be constant. And then with a few more, we can determine where this the lightning strike. Right. Now extend this into three-dimensional. We have a globe, the Earth right here, a bunch of satellites flowing around. If we can have 4 satellites, we can determine the location of that. And so every 2 satellites, we can form an elliptical surface, an intersection of all of those. So we need 4 satellites to determine the location. By the way, when I'm talking about the location, it is also the distance from the Earth. So if we have 4 satellites, we can measure the distance from that point to the satellite. So the GPS is nothing like, it is nothing more than a receiving device. It will receive the signal from all of the satellite. It needs 4 satellites. When we have 4 satellites, to take the distance, the difference of all of that, it will can generate a bunch of hyperbolas, intersection of all of those, give us the location. So 4 satellites to determine the location. If we need 3 of them, we know on the surface. If we're in a very tall building, we need 4 satellites to determine the altitude. So if we have the signal from 4 satellites, and we will be able to calculate where we are on the Earth. And not only that, what is the altitude from the surface. Right. Other than that, the equation is going to be in this form. if we start with x squared subtracting, this is going to be horizontal. So vertices, foci, and center on the same line. If we have the y square first, it's going to be vertical. Vertices, foci, and center on the vertical line. And that line is called the transverse axis. Right, just have one example here. Find equation of hyperbola center at the origin, so center is still 0, 0. And the vertices plus or minus 3, 0. Meaning that we go 3 to the left and 3 to the right, and the vertices. So we will have one vertex is here, and one vertex is there. Next, foci plus or minus 5, 0. So we'll 5 units on the left and 5 units to the right, because on the x corner. So we will have the centers is here. So one focus here and one focus there. Now the distance from the center to the vertex, is going to be a. And the distance from the center to a focus is going to be C. So in this case, C is going to be the biggest one. I forgot to mention that. C squared is the biggest one, so equal to A squared plus B squared. So C squared, the distance from center to a focus, is the biggest one, equal to A squared plus B squared. 5 squared, 3 squared plus B squared. So B squared, 5 squared, 25 minus 3 squared, 9 is 16. So B is 4. Right. Or just 4, doesn't matter. So which means everything lined up vertically except for B is going to be perpendicular to it. So we have 4 up and 4 down. With that we have the box. So 4 up and 4 down, 3 left and right. So we will draw the box. So 4 left, 4 up and down, 4 up, 4 down, 3 left, 3 right, and then we can draw the diagonal. Will give us the asymptotes. And the hyperbola will go through the vertex and approach into the asymptotes. So that is the hyperbola. So we have everything here. So we know everything lined up vertically. So this is the everything lined up horizontally. So this is a horizontal ellipse. And if we want to write the asymptotes, equation of asymptotes, y equal to plus or minus 4 up, so rise over run. So I have equation of asymptote as well. So those are all the information. After all, what is the equation? Right. This is horizontal, so we start with x squared minus y squared equal to 1. This is horizontal. If it is a vertical, we start with y squared minus x squared. And then we have 3 left and right. So we're going to put 3 at the bottom of the x, and then square. And then 4 up and down, put that below y squared. And that is the equation. Equation of the hyperbola. So it's characterized by the minus. X squared first is going to be horizontal. Right. Right. Now, more on conic section. Now we can define the ellipse on the conic section differently. So now if we have a line is fixed, that kind of the directrix. So line is fixed, a point is fixed. And if we define E is called the eccentricity, is the ratio of PF over PL. So in general, we just have a line the line is the directrix, and then of course then the axis is perpendicular to it, and we have on there a point F. We might have an ellipse here. That's about right. Or if we cut this right in the middle, cut this in half, we might have the parabola. Or we might have even bigger than that, kind of here is parabola. Right, so if we take the ratio of the point P, so let's say in this case, in the special case of the parabola, we have the point P, P to F and P to L. If the ratio is 1, that is the parabola. So that's why I said equal distance here to there. Give us the parabola. If it is the distance that, if the ratio here, if it is bigger than 1, so the ratio, the line to the focus is longer than to the directrix, in that case we have the hyperbola. Hyper means more than 1. Hyper. So bigger than 1, hyperbola. If that distance is smaller than 1, meaning the distance from a point to the focus is shorter than from that point to the directrix, then we have an ellipse. So it will be, in general, it will be like this. And usually in the, for example, the sun is at focus and the earth will travel around it. So it's not exactly so the earth traveling around the sun in the elliptical orbit. and where the sun is one of the focus. So it's not very wide like that. It might be more circular, where two foci are kind of close to each other, and the Earth will travel around that. Right. And then on different one, will have different orbit. So the sun is just different orbits. So the sun is not in the center, the Earth going around. Actually, the Earth going around the sun in the elliptical orbit, where the sun is one of the focus. Was that shown by the Kepler's law? Anyway, so different form, and if we want to write this in different form, we can write the polar coordinates. The coordinates will be given in this form. Right. Now, the last thing we'll do is just convert this from polar form into rectangular form. Right. So let's say that in this case, what we do is we'll cross multiply. This is over 1, and then cross multiply. We have r times 2 plus 4 cosine theta equal to 8. Just cross multiply, and we have that. Now, how can we simplify this? Remember, we only have this x squared plus y squared is r squared. Tangent is y over x. I put asterisk there just to make sure that you check the quadrant. And then x equal to r cosine theta and y r sine theta. So those are all we know between rectangular and polar equations. Right. Now do we get that? Let's multiply it out. 2r. By the way, when all of this, why don't we divide everything by 2? Right? That simplifies a lot. Because all of them are even. Why don't we divide by 2? So we have r1 plus 2 cosine theta equal to 4. So factor out the 2 and cancel the 2. This is what we have. A lot better. Multiply them out. R plus 2r cosine theta equal to 4. Now what can we do? We can square it. If we have r squared, that's x squared plus y squared. That's nice. However, r cosine is also x, right? So what we do here is we say r plus 2x equal to 4. We can move the 2x on the other side. We have r equal to 4 minus 2x. And now we can square both sides. When square both sides, we'll have r squared equal to 4 minus 2x squared. Right? Yeah. So for r, and then when we have r squared, we're going to turn that into x squared plus y squared. Put a square outside, and we can multiply around and simplify. We should be able to have equation of a conic section. So once again, cross multiply to get this into one line. We can simplify if we can. So we do that, divide everything by 2, and I put that. And then multiply them out, move everything on one side. That's what we have. And so this equation have x and y in it. So that in rectangular form. We can do the same thing for the next example. Over 1, and then cross multiply r times 1 plus sine theta equal to 2. By the way, it's nice to at least graph this, see what happened. By the way, radian polar, that's good. 8 divided by 2 plus 4 cosine theta. Right. Let's say we go from 0 to 2 pi, and let's go with pi divided by 100. So we go extremely slow here. What's that? Right. Also, radian mode polar, so that's right. Zoom number 6. So actually this is a hyperbola, but because the way it works, it tries to connect all the points. So we don't have the asymptotes here, we just have the parabola. Right. Right. Now, what is this equation? 2 over 1 plus sine theta. That is a parabola. Right. Now let's just simplify this. Multiply them out, r plus r sine theta equal to 2. R sine theta is y. So here we have r plus y equal to 2. Solving for r 2 minus y. Square both sides. Now here, this one is simple enough. I actually can simplify it. R square give us x square plus y square. Two minus y square. Right. Multiply this out. 2 minus y square. I just saw this. A minus b square is that. So it's going to be 2 square minus 2 times 2 times y plus y square. So we have x square plus y square equal to 4 minus 4y plus y square. Cancel out. We have x squared equal to 4 minus 4y. If we factor out the negative 4, x squared equal to negative 4. And factor out, so we have negative 1 plus y, or x squared equal to negative 4, y minus 1. So of course we see this form, which is the parabola that open down, and the vertex will be at x equal to 0, y equal to 1. So we see on this parabola, the vertex is 0 and 1. The focus will be at 0, 0, and proper go around like that. Right, so this is how we can convert from a polar to rectangular form. Just so for our first, in terms of x and y, then we can square both sides. Do not square at this stage. It will be a mess if we square both r and y at the same time. Isolate r first and then we square. And then this one's simple enough, so we can just go ahead and simplify, and we end up with that equation. Right. So that's all I want to cover for this section. And actually, that's all I want to cover for Calculus 2. So, thank you for watching all of these videos, and good luck on your final exam.